Okay, the agenda today is to introduce what are called antiderivatives and integrals. We have done derivative or differential calculus, but now we're looking at what is called integral calculus. We're going to study today the basic rules of integration. This is a huge idea. What we do today is the foundation of this entire unit, and every application we will study will require you to master these skills, so let's do our best. Let's begin with a flashback. It's difficult to talk about integral calculus without talking about differential calculus. So let's go all the way back to the beginning of calculus when we had basic functions and we talked about what is the derivative of those functions. As you may remember, when you have a basic function like this with a power, we take a derivative like this. That power value, the exponent, drops down in front, there it is, and then the exponent value is decreased by 1. So the next one would be 5x to the 4th. And the last one here would be 28x to the 27th. So these are the functions, these are the derivatives of those, and that rule was called the power rule because we're dealing with an exponent or a power. The power rule, you may remember, looks like this. We have a function with some power n. To find the derivative, remember this symbol for derivative here, f primed, we drop that n to the front, drop the power to the front, and we decrease the power by 1. That was the power rule, and we're only looking at this rule today because the power rule is the thing that's connected to some basic rules of integration we will learn today. So let's look at the power rule for a few more examples because these are some tougher ones that we looked at that you may need to help you with your work today. So given each function, find the derivative. Here's a function f of x, like this. Let's find the derivative. So again, you're going to drop that power in front, but now there's a constant in front, or a coefficient in front, so that power will multiply the coefficient, right? So we have 3 times that 1/3, and then the power here has dropped by 1. Now 3 times 1/3, as you know, should cancel because it becomes 1, so we just have x squared. So again, that 3 went here, multiplied that became 1, and this became x to the 2nd power. All right, that's what you do when you have a coefficient. Let's look at function g of x. Now the x is in the denominator of this fraction. As you may remember, when we have a variable in the denominator, we can bring it to the top of the fraction like this. So the 5 remained in the bottom, but that x to the 7th power jumped to the top and became a negative exponent. So now we have a form of this function where we can take the derivative. So g primed, or the derivative, would be, you take that -7, you drop it to the front, we still have our 2/5 fraction here, and then the exponent didn't become 6, it became -8 because remember you always have to subtract 1 from this exponent. So -7 subtract 1 is -8. This can all kind of combine into this. This -7 times 2 is 14. There's a negative sign there in front. The 5 is there. The x to -8 also dropped to the bottom of the fraction because, again, we don't want to keep negative exponents. We're going to rewrite it like this. Hope this is jogging your memory. Let's look at one more. We have function h of x, and it is the 4th root of x. This one, again, we should change to a different form before taking the derivative. As you may remember, when you have roots, they become exponents like this. So we have a 4th root, it becomes an exponent of 1 to the 4th. Now we can take the derivative. I'm going to remind you of the other notation for derivative. Instead of writing it like this, we can write it like this. dh, so we put this here, dh over dx. So the derivative is, we're going to drop that exponent to the front, so there's the 1/4. Then we're going to subtract 1 from here, and when you subtract 1 from 1/4, you get -3/4. That can be rewritten like this. Again, we don't want the negative, so we bring that to the denominator with the 4. That 4 and now has been joined by all this. This, however, the 3/4 fraction tells you it's going to be a root as well. So there's the 3 because it's like a 3rd power, and then the 4 on the bottom tells you it's going to be a 4th root. So just talk about those with your partners if you need. That was just a reminder of some basic power rule applications. We'll need those skills today as we move on. So let's take some notes. You've been provided with a notes page about integration. Let's go to that now. Okay, introduction to integration. The reverse of finding a derivative is known as finding an antiderivative. That word makes sense. Antiderivative is the reverse operation. So for example, we have this function here. To take the derivative, it would become this. Again, by power rule, that 2 would drop down here, and we have 2t, and that exponent would be 1, so just 2t. And if you remember, when we just have just a variable, it becomes 1. So that derivative is that. Now, if somebody gave you this and said find the antiderivative, that process would take you back to the original function. So derivative takes you this way, antiderivative takes you back. So remember, antiderivatives are the opposite of differentiation, or opposite of finding derivatives. So let's take a look at these. What would be the antiderivative of each of the following? So here's a function, the antiderivative. So in your head, you're thinking, what would I begin with and then take a derivative of that to get this? So let me show you this. This is x squared. If you took the derivative of that, that 2 would go in front and you'd have 2x. So that would take you there. So if the derivative of this takes you this way, then the antiderivative of this takes you this way. So start thinking now, what would be a rule for that? How would you go from this to this? Because we already know the derivative going from here to here, but how would you go from here to here? Well, instead of subtracting an exponent, right, you'd be adding one, right? It grows. Instead of decreasing an exponent, it's growing. But also I wanted to introduce another idea here before we look at the actual rules. This antiderivative should actually be written like this. It has this c here. And we'll talk about what this c means right here. So why does this c included in the antiderivative? Here's an example of another function. Or the same function as this. So we have f of x equals this. Let's say you had to find the derivative of that. Well, I just showed you the derivative of that would be 2x. So that makes sense. That means the antiderivative of this could be this. But let's say we had another function, g of x, that looked like this. What would be the derivative of this? The derivative of that would be 2x as well, because that 2 would drop down here and you have 2x. And if you remember, derivative of a constant is just nothing. So the derivative of this is 2x. So it turns out that the derivative of this function is 2x, and also the derivative of this one is 2x. And actually, there will be an infinite number of functions that look like this. You could have plus any number here, and they would all produce the same derivative. So that's why when we do the antiderivative of 2x, we say it is this, because the original could have been any function x squared plus whatever, right? X squared plus any number could have. So we account for that. We say we recognize there's some unknown constant that could have been there that we'll never know what it is here, but it was there, and it can be any number. Okay, so let's find the antiderivative of each of these, and then you will create a general rule. So I'll help you get started on a couple, then you'll check if you can do a few more, and then see if that can lead you to the rule. So let's try this one here, antiderivative of that. Again, if this was a derivative problem, you would just drop the 2 down and decrease this by 1. But we're not doing derivative, we're going the opposite direction. So instead of decreasing this exponent, it should increase. So let me show you the antiderivative. It is this. So the exponent has increased. And we'll talk about what to do with this 3 in a moment. But basically, when you look at this, the way to check if it's correct is take the derivative of this, and if it brings you back to that, and you know this is the proper antiderivative. So what's the derivative of this? Well, you would drop the 3 down, and this would become a 2, so it matches. So if the derivative takes you this way, then the antiderivative goes this way, and it works. So how about the next one? Hopefully you got that. Again, we increase this exponent by 1, and we have the antiderivative. And having that 4 there helps, because as you notice, if you took the derivative, dropped the 4 down, there's that 4, this becomes 3, so that works. The next one, and the next one. All right, there's obviously a pattern here, and clearly I've chosen these very specific coefficients in front to make this work. So this one's going to be a little bit different. What's going to happen here? There's no number in front. You do know you're going to have to increase that to x squared. But will that work? If you just wrote x squared, would that then going backwards would it create this? Think about how you can get rid of that number. So think about this for a moment. Let's see what you come up with. Okay, so here it is. This one may have been tougher to figure out, but hopefully some of you did. This is the antiderivative. Think about this now. If you take the derivative of this, you would drop that 2 in front, and that 2 would then multiply by this half and cancel away. And that's what we have here. We have just an x. We don't have any numbers in front of it. So that 2 cancels this half, and this becomes just x. And there it is. So how about this one? What would you do here? All right. I hope you came up with that. As you notice, this has to go up by 1. So there's the 3. But you needed some number in front because, again, if you took the derivative here, that 3 would jump to the front and it would multiply by this number here and become 1 because there's just a 1 in front of this x squared. So I hope you were able to come up with this fraction here. That fraction needs to be there for the antiderivative to work, right? Because that will multiply by that. So now try this one. All right, so after doing a few, I hope you got the pattern there. But basically, there it is. If you drop this 4 in front, if you took the derivative of this, that 4 would go in front, it would cancel away with that 1/4, and we'd have x cubed, and there it is. So now what's a general rule? If you have x to some power n, could you write a rule here using n for finding the antiderivative? All right, there is our rule. This is a fundamental rule of integrals. We won't learn that many rules of integrals. This is a key one that will take us through the whole unit. So just take a look and make sure you really understand all these examples and how it led to this important rule here of integration. All right, the rule is basically you're going to add 1 to the exponent here and then multiply by a fraction with 1 over whatever that number is. Okay, so let's take a look at this one. So what would be the antiderivative of this? All right, hopefully you got that. By the rule, we're supposed to add 1 here and then include a fraction in front that is 1 over whatever we've added here. Because now if you did a derivative of this, that would cancel away that fraction. And don't forget the c. Why c? Again, we talked about this, but I'll show it with this example. If you had this function, that the derivative of that would be x to the 10, because that 11 would cancel that. That would become x to the 10th. That 4 becomes 0. So there's that. But we could have another function that has the same beginning part, another constant value, and that would also have the same derivative. So again, that's why we have the c. Next one, how about this one? This one's going to be a little tougher probably. In this case, hopefully you noticed you have to do that rule about bringing that up like that. Now you can look at this and use our integration rule. And there's our integral plus c. In this case, right, we added 1 to here, but when you add 1 to here now, it becomes -4. And by the same rule, we put a fraction in front, and this became -4. Therefore, we have a fraction with -4 on the bottom, but the negative can be written here. Now think about taking the derivative of that. -4 multiplied in front here, it would cancel all that, and then this would become -5. So we're back to here. So the derivative of that would bring us back to this. And this can be simplified into, we're going to continue on the bottom now. So to recap some things, the process of finding a derivative is known as differentiation. So that's what we did when we did calculus before. We did differentiation, or we found derivatives. The notation for finding a derivative is this, right? If we want to find a derivative of this, we can write dy dx, or you can write y primed, right? So for example, if we had this function and we want to find the derivative, we can write dy dx equals, and we find the derivative of this. Again, the power rule tells us we drop the 5, that becomes 15, that decreases by 1, this 2x becomes a 2. That's derivatives. And now let's recap antiderivatives. So the process of finding an antiderivative is known as antidifferentiation, also known as integration. So now we are doing integral calculus. The notation for finding integrals is this. Okay, so you're already finding some antiderivatives, but now we're going to use the proper notation. It's this sign here, which looks like a giant S in a way. and then you put your function here, and then you always end with dx, or whatever the variable in the function is. It might not be x, it might be something else. If the variable is like a t, it would say dt, for example. It is called the indefinite integral. So this symbol or this notation here is called the indefinite integral. And you'll see what a definite one is soon, but for now, this is what we're going to use. So here's that function, and we're going to find the integral of this function. So we're going to put that function in there, and now writing it like this basically tells us, let's find the antiderivative of this. And the antiderivative of this is that. We know by the rule of integration that you're going to add one here, not subtract. That was derivatives. We're going to add one here, so it becomes a 5. Then you're going to multiply this by 1/5, and this multiplied by 1/5 is actually 3. And here you're going to increase the x, which is now x to the 0. You're going to make an x to the first power, which is this. So there's our antiderivative of that. And don't forget the c. So that's a recap of what we've talked about so far. Now let's look at the basic rules of integration. So first of all, the power rule. We've already done that rule, but here it is. We're just going to reiterate that rule. We have an integral of some function with an exponent, and the integral of that is this, plus c. And please know that n cannot be equal to -1. This will not work if this exponent was -1. We can talk about that later. Here's an example of this. We have this. So this is a simple example. This is one that, based on the work you've done so far, you should be able to do. So find the integral of that. Let's see what you get. Okay, well, the integral is that. Once you're used to the rule, you don't have to write this 6 plus 1, 6 plus 1 here. You can go straight to what is the integral. And as you know, this goes up by 1, and then we put a fraction in front, 1/7. So if you went straight to that, great. This is just showing you the step here. Okay, so the power rule is the basic rule. Now let's move on from that with some other rules. There's something called the constant rule. It looks like this. So if you take the integral of a constant, this k represents a constant, then the integral of that is kx plus c. For example, here we are taking integral of just 4. There's no x or anything here, and actually it says dt. That means if this was a function and it had some variable in it, it would be t, but all we see is a 4. And the integral of just a constant is that number with the variable added. If this said dx, you would put 4x. If this said dt here, so we put t. But basically, this is the antiderivative of that. And the reason for that, if you look at this and you want to go backwards, remember to start here and go to there, we take the derivative. If you took a derivative of this, if you remember when you have just x or t or whatever to a power of 1, that derivative of that just becomes the constant 4. So that makes sense there. Going backwards, we can see why the constant rule works. Next one, the constant multiple rule. The constant multiple rule gives us this. So if you have a constant and you multiply it by a function, then to find the integral, you can just bring that constant out and just find the integral of the function and multiply by the constant. We had a similar rule in derivatives. Let's take a look. An example of that is this. You have an integral of this. Here's a function x to the 5th. Here's a 3 here, that constant in front, or a coefficient. We can bring that coefficient out like that and just worry about finding the integral of that. And the integral of that, using our basic power rule, is this. Again, you don't have to write the 5 plus 1. You can go straight to knowing that this is x to the 6th. And then if this is x to the 6th, then you have this fraction in front, 1/6. But that 1/6 kind of combines with the 3. And 3 times 1/6 is 1/2. So please make sense of what's going on there for yourself, but basically you're just canceling the 3 in this fraction. And you get that. And they write it kind of funny here with this C1 and then 3C1, because it's just showing you that you take that 3 and you actually multiply it, because if you're taking the integral of that, there's the integral and there's that C value, and you still have that 3. You have to multiply 3 through on that constant. But that constant can be any number. And that 3 times any number produces any number as well. So basically, it doesn't matter. Like 3 times whatever random number is some random number anyway. So in the end, we just end up putting c there. Okay, next one, the sum or difference rule. The sum or difference rule tells us if we have one function plus or minus another function, and we're trying to find the integral of all that, we can just do the integral of one function and then the other one. So basically, you can like separate it, the integrals of the two pieces separately. For example, we have this long function here. This function has 3 distinct parts, right? So we don't have to worry about some weird integral for all. We can just do the integral of this part, this part, this part separately, and just that's our answer, right? We can treat it as integral of these 3 separate functions. And then each of those has this constant or this coefficient in front. So this one, the 3 came out, this one, the 6 came out, this one, we have that. But once you get used to this, you don't have to worry about writing all this out. This is just showing you how it all kind of breaks down. But basically, when you look at this, you just take the integral of each portion separately, right? So if you take the integral of the first part, that goes up by 1, so it becomes 5. And then you have to put a 1/5 in front. So here we can see that happening. We have u to the 5th power here. Let me go one more because you can see the final answer. It might be easier to even go from here right to the final answer. There's all these intermediate steps to show you the way it's done, but hopefully you're ready to just go from here right to there, which is fine. So this goes up by 1, and then you have to multiply by 1/5, right? So here's the u5, and then 1/5 times 3 became 3/5. And this one here, this goes up by 1, so it becomes u to the 3rd, but then you have to multiply by 1/3 power, sorry, not 1/3 power, 1/3 fraction, right? Because when this goes up, we need that fraction, and 6 times 1/3 is just 2. And here we have a constant, and the rule is when you have a constant, you take an integral, it just becomes 2, and whatever the variable is, plus c. Okay, so again, these steps is just overkill in terms of showing you how it's done, but you can go right from there to there.
All right, you're doing it. Getting through this long, tough lesson, but here we are. It's time now to practice the skills we've learned. Let's try some. So this is taken directly from our practice assignment. We're going to look at one problem from each of these questions here, and then you can try the rest. So in question 6, we're going to look at part C here. We are asked to find the integral of 5x dx. That means the antiderivative of 5x. And that is this, right? We know the rule is the basic power rule. We go for integration, we go the reverse of derivatives. If this was a derivative problem, differentiation, we would drop the exponent and reduce by 1. But now we're doing the opposite process. We're going to raise the exponent by 1 power. Currently it's x to the 1 power, so I made it x squared. And then you multiply by 1 over the new exponent, 1 over 2. That's it. That's all there's to it. This simplifies into 5 over 2 x squared plus c, of course. Okay, so now pause and try the other 3 or 4 in question 6. Okay, let's go to question 7. Oh, first of all, check your answers for question 6. Here they are. And you should clearly see a pattern in these questions, right? All the problems in question 6 are all x to the 1st power, so there should be a pattern emerging there. In question 7, look, they're all x squared, so we're going to look for the pattern there also. So in question 7, we're going to do part E together. Let's take a look. So the integral of x squared over 3, which you can think of as the same thing as 1/3 times x squared. Sometimes it's easier to imagine it like that, because if you think of the 1/3 in front of there, you just look at the x thing and do the rule to that. So the rule again is we're going to raise this power by 1, so x squared becomes x cubed. And now we multiply by 1 over the new power, 1 over 3. So we have 1/3 times x cubed over 3. Notice on the bottom we have a 3 and a 3. Those will become 9 when you multiply. So we have x cubed over 9 plus c. Great. Try the remaining problems in question 7. And now check your work for those. Hopefully, again, after a couple, the pattern was clear and you're working quickly through these. And number 8. Now the powers are all powers of 3. 3rd power cubic. All right, let's do D together. Same approach. We have 4/5 x cubed. I'm going to raise the power by 1 to make it x to the 4th. Therefore, I have to multiply by 1 over 4, which I'm doing here. Now, when you combine these fractions through multiplication, the 4's cancel, and you're left with just 1/5, which means x to the 4th power over 5 plus c. Okay, pause and try the remaining problems in 8. Again, after you do a few, you'll quickly see the pattern, and you should move very quickly. And check your work for those. Okay, let's do a few more. So first one is very similar to what we just looked at. Again, we're looking for a definite integral of this. Now it's a 5th power. Give it a try. And now let's check. Raise the power to 6, multiply by 1/6, and therefore x to the 6th power over 24 plus c. Okay, b. In b, you have multiple terms in there, but remember when we're doing integration, you can just do the integral of each term one at a time. So just apply what you know about integrals here, here, and here. Let's see if you can get that. Okay, so the first one, I raised the power by 1, became x cubed, and then I multiplied by 1/3. And notice I didn't even show that. At this point, hopefully you're doing these steps in your head. So again, when this became a 3, I multiplied by 1/3. 1/3 times that becomes a 6 there. Second term, the power is 1. I raise it by 1, it becomes 2. So I multiply by 1/2, which is what this has become. There's 1/2 has been multiplied, so now it's over 2. And the last one, whenever you have a constant, it's like having x to the 0 power after it, because x to the 0 power is 1. So -1 really means -1 times x to the 0 power. And x to the 0 power raised by 1 makes x to the 1. So here's that -x plus c. The last one. In the last one, you have to think about this one. You have the variables in the denominator. So remember, with those, we can bring that up, and it becomes x to the -2 power. And then just apply the rule we've been using to find the integral. Let's try. And now let's see how it went. So that, again, can be raised to the numerator, becomes x to the -2 power. And then the rule is add 1 to that. Common mistake is changing this to a -3. But that's not what it is. When you add 1 to -2, you get -1. So there's that. And that means if you had -1 as the new power, you have to then multiply by 1 over -1, which just is the same as a negative applied to the front here. This, of course, you can rewrite like this by moving the x with the negative exponent back to the denominator. Okay, great. 3 problems that are not so bad, but they really do check your understanding of this new rule you learned about integration today. Couple more things. So 2 more problems. One is this. We have a unknown function, y equals f of x. We know it passes through this point. We also know the gradient of this function or this curve is given by this equation. So in other words, we know the derivative function, and it asks us to find the equation of the original curve, the original function. So if we know the derivative, we want to go backwards to get to the original function. And the process of going backwards from derivative to original is finding the antiderivative. And that is what integration is all about. So what you're going to do in this one is find the integral of this derivative function it gave you, because that'll take you back to the original function. So try that now. Let's see what you get. Okay, let's check your work. So here's the integral of the derivative that it gave us. And that becomes 2x. This one again is like 2 times x to the 0 power. So it becomes x to the 1 power, there it is. This one, we have 1/3 times x, raise the power, and there's the 1/3 times that, and then it becomes this. So there's our original function. However, the original function has some c value, and we talked about that. C can be any number, so we don't know what that number is. This represents many possible functions, but we are told that the function we're looking for passes through the point 1, 3. So we know that point will help us get the exact equation for the function we're talking about, because even though this represents infinite different functions, there's only one of those infinite functions that passes through this point. So let's use that point to help us. Substitute in for y and x here to solve for c. Okay, so we put in a y value of 3, because that's what we have here, and an x value of 1 right here. And we get this. Solving, we get 5/6. Therefore, we know what c is now, and there's the single function that must pass through that point. Great. That's a little tougher, I guess, but it is a common and important application of what we know about integrals. Okay, last one. So we have this problem here, and same idea as the last one. We have a derivative. This, again, remember, means derivative, so it's the same thing as saying we have a derivative. So here's a derivative function, and again, we're given a y and x value of the original function, and we want to find the original function. So same process as the last one. Let's try. Here we go. Take the integral of the derivative to get the original function y. So the integral of that it gave us, the derivative, becomes this. Check your work on finding the integral here. Okay, and again, we're given a point. So we're given the point 3, -1. So -1 for y, 3 for x. Solve, 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 you get c, and now you have the equation, the original equation. I think I said last one, but there's one more. This is the last one for real. So now we know, we're going to look at how we can apply this idea. So let's say we have a cost function. And, oh no, sorry, we want a cost function, but we know the marginal cost function. And we've talked about that before. Marginal costs are like the costs at a moment in time. Therefore, marginal costs come from taking the derivative of a cost function. So this function we're given here, the marginal cost function, is the derivative of the original cost function. So we're going to do the exact same thing we just did. We have the derivative. We want to go back to the original, in this case, the cost function. So take the integral of this and see what you get. Okay, so we take the integral and we get this. So this is our original cost function. Again, we have this unknown c value, but we are told there's a fixed cost. The fixed cost is 40. The fixed cost on a cost function is the cost at x equals 0. When no units are produced, that is the cost the company incurs. So x is 0, y is 40. Put that in there and solve for c. Check your work. We found out c is 40. Well, therefore, we know that this model must be x plus x squared plus 40. All right, great job. You have learned integrals, and you have come to the end of our unit and perhaps the end of our course. Great job.